Greetings of the day, dear students. In this video, we are going to discuss about the principle of operation of three-phase induction motor. In this video, we will discuss its principle of operation, right? So here, just like alternator or synchronous generator, where we are having there a stator and a rotor, here also we will be having two components. One is the stator and rotor, right? For the stator, we used to give the outermost, this one is the stator, right? And if this is the rotor, for this stator we used to give the three-phase supply will be given. Because of the given three-phase supply, the flux will be established. And because of each phase, three individual fluxes will be established, but overall we will have one resultant flux phi r, which will be rotating, right? So here, because of this rotating flux, which is already rotating at synchronous speed, it is rotating at synchronous speed ns. Now here we are having a rotor initially, which is at stationary, right? And already we are having conductors placed in that. Now this flux passes through the air gap and sweeps the rotor surface. As and when it sweeps the rotor surface, it is going to cut the rotor conductors. This is very, very important. I repeat again, because of the applied three-phase supply, right, the flux is established, and this magnetic flux will be of constant magnitude, but that flux will be rotating at synchronous speed. Now this flux is sweeping the rotor surface where we are and it is going to cut the rotor conductors, right? Now there is some relative speed difference. There is a relative speed between the rotating flux and the stationary conductors. This is very, very important. Because of this relative speed, right, between the rotating flux and stationary conductors present in the rotor, an EMF will be induced according to the Faraday's law of electromagnetic induction, and an EMF will be induced, right? Now the induced EMF frequency will also be equals to the frequency of the supply. Now whatever the voltage or EMF is induced, that induced EMF frequency will be equals to the frequency of the supply. Now magnitude wise, it will be proportional to the relative velocity between the flux and the conductors. Coming to its direction, it will be given by the Fleming's right hand rule, right? Now here, because of this induced EMF, what happens? There are some conductors present in the rotor, or since the rotor bars are conductors which are going to form a closed circuit, now the current will be produced. So here, for example, if you are having a rotor conductors, right, and the flux, the rotating flux or resulting rotating flux or revolving or rotating magnetic field, right, has cut these conductors, right? Because of this relative speed between the flux and the conductor, some current is induced. Now because of this current, one more again flux will be generated, right? It is simply like this. Initially current is passed through the conductor and the flux is established, and this flux is cutting the stationary conductors, and now because of the relative speed, again an EMF will be induced. As these conductors are forming a closed circuit, again the current will be circulating. Now because of this current, again flux will be generated. Now this flux is going to oppose the cause. This flux is going to oppose the cause. What is the cause for its production? Relative speed. What is the cause for this flux? That is the relative speed. Now In order to oppose the cause, what happens is the rotor will be slowly set into the motion. It gains speed and it tries to catch up the rotating or revolving magnetic flux, such that the speed it tries to minimize the relative speed. It tries to minimize the relative speed, because that is the cause. That is the cause. Now this induced EMF, because of the induced EMF, current is produced, and that current again produces the flux, and that flux opposes the cause. The cause is here nothing but the relative speed. In order to oppose that cause, what happens? The relative speed value must get decreased. So for that sake, the rotor tries to rotate and tries to catch up the rotating or revolving magnetic field, right, which is at synchronous speed. But it cannot become equals to the rotor speed cannot become equals to the synchronous speed. That is the reason why in three-phase induction motor, this is also called as asynchronous machine. It is also called as asynchronous machine, right? This is how it gets operated, right? So you can observe here, of course we are having two types of induction motors. One is the induction machines, one is the single phase also we are having, and three-phase induction motors we are having. And the rotor, it can be divided depending upon the type of the rotor, whether it can be squirrel cage motor or slip ring motor or wound type motor. This is also we are having. And as I told you, we are having the rotating magnetic field, right? And here the speed, the rotational speed of the rotating magnetic field is called the synchronous speed, ns. That speed is given by 120 f by p, where f indicates the frequency of the supply and p indicates the number of poles. Right? And one more important terminology, slip. Here we will come across one word, slip. S is defined as, percentage slip is defined as ns minus n divided by ns. For example, if this is the stator and if this is the rotor, and now this is already the flux is revolving or rotating with speed ns, but here the difference between the rotor speed and this flux, ns minus n divided by ns is called into 100, is called the percentage slip. In this formula, ns is the synchronous speed and n is the actual speed of the rotor. Now the difference ns minus n divided by ns into 100 is called the percentage slip. If both becomes equal, of course here it is not possible. If ns is equals to n, then what happens? Slip becomes 0. Right? If the rotor catches up the stator speed, there won't be any relative speed between the stator flux and the rotor, hence no induced current will be there. So if there is no induced current, no torque production will be there to maintain the rotation. So however, this is not going to stop the motor. The rotor will slow down due to the loss of torque. When it has little bit slowly slowed down, again there will establishes a relative speed. Is it clear? As and when it has, if it has become equal, what happens? There is no relative speed. Obviously there won't be any induced current, there won't be any torque. So all of a sudden it will not stop. Slowly it slows down. Once rotor got slowed down, again there establishes the relative speed. Like this it goes on, right? So this is why the rotor rotates at speed which is always less than the synchronous speed. It is always rotor rotates at a speed always less than the synchronous speed in the induction motor, right? So these terminologies are also important. ns equals to 120 f by p, percentage slip ns minus n by ns into 100. Dear students, ns indicates the synchronous speed, n is the speed of the rotor. in this entire discussion, there must be relative speed between the rotor and flux, magnetic flux. Once there is a relative speed difference between the rotating or revolving magnetic flux and rotor, then you can understand the operation. Because of that difference only, EMF will be induced. Once EMF is induced, current will be produced in the rotor conductors. Now because of this current, again flux will be produced. Now this flux is going to oppose the resultant flux, which is the cause, is going to oppose the cause, which is the relative speed. For that sake, it tries to rotate, tries to catch up the rotating or revolving magnetic flux by trying to rotate at synchronous speed. But it cannot attain the synchronous speed, right? Like that. Thank you.